Today, we have with us Professor Saber N. Elaidi, who is the chair professor at Trinity University, United States of America. Professor Saber needs no introduction for those people who are working in discrete dynamical systems. His book on discrete chaos is so popular that most of the people who do research in discrete dynamical system must have read it. Professor Saber took his PhD from University of Missouri, Columbia in 1978. Currently, as I mentioned, he is the chair professor at Trinity University, USA. He is the president of International Society of Difference Equation, ISDE, from 2005 onwards. He is co-editor-in-chief of the Standard Journal, Journal of Difference Equation and Application, Journal of Biological Dynamics. Both are published by Taylor and Francis. He has published more than 100 research papers in reputed journals. Today, he will speak on extension of Scharkovsky's theorem and related conjectures. May I invite Professor Saber for his lecture. Professor Saber, please.
Thank you very much, Vinod. I am very happy to be here. This is my second participation in the workshop in your university, and unfortunately will not be able to be there physically. It is 11 p.m. at night in Texas, in San Antonio, Texas. So this is kind of late, but it's okay. That for you guys, it is the morning time. Okay, so I'm going now to go to my slides. Okay. So this is we'll be talking about non-autonomous discrete dynamical system. In fact, the title is misleading because non-autonomous systems are not dynamical systems. Okay. Autonomous, of course, are discrete dynamical system, but this is a mistake in the literature. So people talk about non-autonomous dynamical system, while it is not a dynamical system. Okay. This is the last time I had the pleasure of lighting the candles, and you see Professor Kumar over there, and the president of the university is there, and Bob Devani is there, as you see. Unfortunately, we are not able to do this time. So we are going to talk about the issues of introduction, skew product dynamical systems, periodic systems, one-point compactification of function spaces, and topological properties of omega limiting sets, and extensions of Scharkovsky theorem, and some new directions and open questions. And you can always interrupt me and ask questions. Of course, you are muted, so it is chatting. So the theory of non-autonomous have been developed by many authors, okay, including late Professor Olbach, unfortunately he died, and his students, and Peter Kloiden, and his collaborators investigated the limit sets of non-autonomous systems that are asymptotically autonomous. The special case here is also of an autonomous periodic discrete system. Periodic means the basically the system have finitely many maps instead of infinitely many maps, finitely many maps, and these maps are periodic of certain period. And this theory was developed by myself and Professor Bob Sacker, the famous Neymark-Sacker bifurcation theory, and the references there by Claudia. So other people also investigated that. Some put some conditions only for two maps, two periodic, they call them alternating systems. It has been shown by LaSalle and Dowker and Friedland that the omega limiting sets of an autonomous discrete dynamical system is invariantly connected, not connected. Now, if you study differential equations, this is the omega limiting sets are actually nicer. They are actually connected sets. Unfortunately, for the discrete dynamical system, the omega limiting set is not connected, is invariantly connected. And this invariantly connected, it means that that the omega limiting set cannot be the union of disjoint invariant connected sets instead of just invariant, instead of just connected. It must be invariant open set. Sorry, invariant open set. So it cannot be the union of invariant open sets. Unlike just the definition of connected set. So we want to see if we can go further, extend this to non-autonomous dynamical system, discrete in particular. And here we're talking about semi-dynamical systems, where the action is the non-negative integers. So it is semi-dynamical system, not the whole integers. Okay, so then we will see if we can, the phase space is assumed always locally compact metric space. And we can extend this, of course, because of locally compactness to compact spaces through the one-point compactification. Okay. The problem is not just topology here, but it's connected with dynamical systems. So the question, how do you extend the dynamical system to the one-point compactification? This is a rather rough, I mean, not so easy issue, which we will discuss in this lecture. And then finally, since the non-autonomous systems are hard to deal with, we are going to embed the non-autonomous system into an autonomous skew product autonomous system. Okay. Now we will define the word skew product in this lecture, and I will show you how to embed a non-autonomous systems, whether it's discrete or continuous, even the same, or general, actually, into a skew product dynamical system in higher dimension. And okay, full screen. Okay, so it's now, I think, full screen. Okay. So I guess that's one of the things we are going to do. The theoretical result then applied to population dynamics, which are not going to do here, but you can apply it to anything, I mean, in population biology, etc. But here we are not going to do that today. So just a reminder of what we are talking about here. Let's start with a metric space, and T is a topological group. So pi from X cross T to X, okay, and then we call this a dynamical system. If you have the identity axiom pi x0 is X for all X in X, 0 is the identity of the topological group T, and then we assume the homomorphism axiom pi of pi x s t is pi x s plus t, plus here is the operation of the topological group, the group there, and then the continuity axiom, the pi is continuous. Now, if T is a topological semigroup, then we call this triple a semi-dynamical system. What we are going to do today is assume that the topological semigroup is Z plus, the set of non-negative integers, okay? So that's what we call discrete dynamical system. Now, if the set T, the topological semigroup, is R plus the set of non-negative real numbers, then we have differential equation, which we call continuous semi-dynamical system. And of course, the orbit with respect to pi, or it is pi xt, where t is z plus. And then we have the omega limiting set, which is the set of all limit points, okay, of an orbit. So omega x pi is all the z's such that there exists subsequence in z plus where pi x in k converge to z as in k goes to infinity. Okay, or k goes to infinity. Okay, so the theorem on general dynamical system is that if you have a dynamical system or semi-dynamical system in this case, with X is compact topological space or metric space, then for each X the set omega is non-empty, closed, invariant, and invariantly connected. As I mentioned earlier, it's not connected. So this result also is true for X is locally compact, but here we require that the orbit closure of a point is compact. Now, let's connect this with maps, okay? So we start with a action of a topological group in a metric space or topological space. If you can go further to uniform space, if you like. But now we are going down to earth, which is maps, okay? So now, if you have T equals Z plus, the topological group, semi-group is Z plus, then you can generate a semi-dynamical system using a continuous map by letting pi xn equal the nth iteration of f. F to the n means f circle, the composition of f n times. Then the forward orbit of a point with respect to pi is the orbit x of f is f to the n x, where f to the n is the nth composition of the map f. And the subset of x is invariant, f of a equal a. Then you have other notions like positive invariant, negative invariant, etc. if the map is one-to-one. So in this case, you can write the omega limiting set in a different way, where omega x with respect to the map F is the same thing. Instead of saying pi, we say now the map F. And you can prove it is the intersection of the union of the closure of, sorry, the intersection of the closure of the union of F to the NX. That's clear, as that makes it a closed invariant set. Now we are going to do the embedding now. Okay. So XD is a compact metric space. F is the set of maps. F0 infinitely many maps. All these maps from the metric space to the metric space X, continuous maps. And we examine a new semi-dynamical system, which we call the skew product, pi. You take the product X and F. F is the set of maps is in the function space. Z plus to XF, which is defined by the following. Pi XFI 0 is just XFI. That's what we did in defining a dynamical system for any X. And then the critical part is this. Pi XFI n, you move Fi to Fn plus I, and X will go to phi n comma Ix, where phi ni is the composition of the maps starting with Fi and ends with Fi plus n minus 1. And F1i is just Fi. And the diagram below will show you what we are talking about here. So in the top, you have a map pi from X cross F cross Z plus to X cross F. And then you project down. X cross F projects to the function space, the set of maps F. And on the other side, you project by the projection P times the identity map. So you go from X cross F to F and cross Z plus. Now, in the lower part, which is F cross Z plus to F, this is another dynamical system, actually, on the space, in the space of functions F. And sigma is the shift map. So if you take a map Fi n, then it goes to Fi plus n. So there is a shift. Okay. So this is sigma is called in dynamical system the shift map. Okay. So the question is this an autonomous dynamical system, which is X cross F and pi? And the answer is yes. This is an autonomous dynamical system. So we start with a non-autonomous system, which is we have infinitely many maps. It's non-autonomous, not one map. And we embed that into a product space, X cross F. Okay, in this product space, we have an autonomous dynamical system. Okay, so that's really the idea of the embedding theorem here. Okay. So that's just basically saying what we just did is that the setting now is just, it's called skew product dynamical system. And if you put this, the set F as a subset of the set of continuous maps from X to X, okay, then we can have a topology here on the map in the set F. Okay. And this is basically what a picture what we have to do here. So we take the maps, infinite many maps, and we in this picture we assume that the maps in the space function will converge to F uniformly. So if you take a set of maps F union little f, then basically that's the closure of F in the compact open topology, and you get a really nice space here. Okay, so basically you start with the point x0 and f0. So f0 x0 goes to x1, then f1 takes over, f1 x1 goes to x2, etc., etc., etc. And then the maps will converge uniformly to F. So this is a special type of non-autonomous system, discrete non-autonomous systems, where the maps would converge uniformly to a continuous map F. What we are going to do here is to do basically one-point compactification here. And this is a special case of when the maps are finite. So you have F0, F1, F2, Fn, and here we have 6 maps, okay? And then the F6 is F0, so it goes back. So this is periodic. So this is a very special case of the general non-autonomous, and it shows here that we have a x0 goes to x1, x2, x3, and then repeats. So you have an orbit of period 4. So it is a cycle of 4 points, a 4 cycle. And it shows that in the, if you go to start again at x0 back, you need to go period, at least period 8. In the skew product, it will be period 8. So you go 4, then again you repeat x0, x1, x2, x3, and then back to x0 there. So this is the theorem that we can show that if you have a compact metric space, XD, and the maps are sequence of continuous maps, uniformly convergent to F, and you take the space, the set F, and this is, I'm sorry, L dots means dots, but I made a mistake in the LaTeX, and there is another, I guess, misprint. Topology is wrong. There's an extra I there. Then the closure of F is compact in the compact open topology. Okay, so this is from Arzela-Ascoli theorem, basically. You can apply Arzela-Ascoli theorem. And if, again, we can define, extend now the dynamical system to the closure of the set F. So by tilde is X cross F closure. Now F closure is compact in the compact open topology, cross 0 to that, and we just have that definition. So you can show that the extension of this map, I mean of the dynamical system to the F closure is also a dynamical system. So F itself is not compact, okay? But you go to F closure in the compact open topology, then it will become compact. So this is a rather critical theorem that you can extend your dynamical system to a compact spaces here. But if you assume, now here the assumption is that XD is a compact metric space. We don't like this assumption, okay? So we want to go to locally compact and then do 1-point compactification of this, okay? Now, unfortunately, this is doesn't work with the usual definition of locally compact spaces, okay? The is not uh, good for the extension of the dynamical system, okay? It's good for 1-point compactification of topological spaces, but not good for extension of dynamical system. So we have to create another way of looking at locally compact spaces, okay? Otherwise, we get stuck. So this is mixing topology and dynamical system together, okay? So if it's just pure topology, then we just go with the usual traditional definition of locally compact spaces. But now we need something slightly different. So assume the metric space is not compact. And we will define something called Mandel-Kern locally compact, or M locally compact. Okay. Okay. So a space is locally compact according to Mandel-Kern, or M locally compact, if it is the countable union of compact sets, where each set hk plus 1 is the uniform neighborhood of hk. So H1, then H2, H3, H4, and each one is basically HK is a subset of the interior of HK plus 1. Okay, so this is the new type of locally compact metric spaces. Okay. The good news is that this definition is not as bad as it looks. Okay. So, of course, compact spaces will be locally compact in this system, M locally compact. You could also, all the Euclidean spaces will be M locally compact. Open spheres in Rn are locally compact. Any non-void space in which any bounded subset is contained in a compact subset is M locally compact. So M locally compact is not restrictive as it looks here. Okay, so this is the idea of the locally compact M locally compact spaces that we are going to use now. Okay, so why we want this M locally compact rather than the usual locally compact? Okay, this is the reason. Okay, every locally compact metric space has a metric 1-point compactification, and the map I from X to X hat is a uniformly continuous injection, and the homomorphism between X and X hat minus infinity hat. Okay, this is known. Okay, and the main theorem is that what we want is really the next theorem. If you have locally compact space, now we're talking about M locally compact, Mandel-Kern type. If you have a map F from XD to XD, and if that's uniformly continuous, then you can extend that to uniformly continuous map F hat from X hat D hat to the 1-point compactification. And that's really very important, okay, to be able to extend your map to the 1-point compactification, okay, and still uniformly continuous. So this is our main theorem here, is that if XD is a locally compact metric space in the sense of Mandel-Kern, So this is M locally compact. So anything we say locally compact, we mean M locally compact. Then let F be a uniformly continuous, and F hat is from X hat D hat to X D hat be the uniformly continuous extension of F to the 1-point compactification X hat D hat. Then for any X in X hat, the omega limiting set is non-empty, closed, invariant, and invariantly connected. So we basically extended all the properties of the omega limiting set from the autonomous system to the non-autonomous, but for special non-autonomous system, of course, that's asymptotic to an autonomous system. Moreover, if infinity hat is not in the omega x f hat, then omega x f hat and omega x f are the same. Therefore, omega x f is non-empty closed invariant and invariantly connected. Also, okay, so so the main idea here is the non-autonomous system here, okay, that we discussed so far, and we want to do if go back to the idea of Scharkovsky theorem, okay, and I guess it's not the existence of cycles of a continuous mapping of a line into itself, and in this case, I guess the major theorem of Scharkovsky is that basically he got the positive integers order, certain order for positive integers, and this order basically starts with the odd integers, 3, 5, 7, 9, 11, etc. Then you multiply that by 2, 2 times 3, 2 times 5, 2 times 7, and then you multiply by 2 squared, and then by 2 to the n, all the positive, all the odd integers. And then the last one is powers of 2 in decreasing order. So 2 to the n minus 1 to the etc. So the Scharkovsky theorem basically says if you have a continuous map on the real line, this is one-dimensional theorem. Okay, so it says if you have one-dimensional continuous map on the real, and if it has a point of period in any of these strings that we have, then basically then you must have this map must have points of all periods that follow that number. So a special case of this was done by Lee and York. Period 3 implies chaos, means if you have period 3, then you have all points of periods of all periods. And I guess the question is always who did this first, or it's clear that Scharkovsky theorem came before in 1964, and Lee and York came 10 years later. However, I guess the Scharkovsky theorem is now much well known, except now the word chaos actually can be attributed to Lee and York. Okay, that's always a controversy here between these two people. And I think in last conference, we have both people in the same place, okay? And it was, I guess, when we attended last meeting, that the one I showed you at the beginning. I guess first time probably in both people, both York and Scharkovsky meet in one place. And it was really amicable meeting. Okay. Now, the question always, what is the implication of Scharkovsky theorem, and what would be a converse of Scharkovsky theorem? So the converse of Scharkovsky theorem, I actually looked at this in 1996, a long time ago. Some of you were not born yet, probably 1996. And I was in a visit to the University of Augsburg in Germany with my late friend Bernd Albach, and he posed this question to me: can you have continuous map that has a point of period 5 but not 3, a point of period 7 but not 5, not 3? A point of, all these, can you construct such maps? Which, this will be called the converse of Scharkovsky theorem. So Scharkovsky theorem say, if you have for a map, if you have a point of certain period, then you'll have points of all period that follows that order. The question is the converse, backwards. For example, can you have a map of period 2 but no other periods before that? Okay. So, and the weakest, I guess a more difficult question was, can you have points, a map with all periods of powers of 2, but nothing of periods like multiple of powers of 2 times an odd number? And that was discussed later by with somebody asked that question later. Okay, and it was not published, but it is not hard to do. So in converse of Scharkovsky theorem was done. Now, the other question is that everybody will ask at this point. Now, Scharkovsky theorem is working on the real line. Can we have any extension of Scharkovsky theorem beyond one-dimensional maps? And that question basically was answered partially. Of course, as you know, there are many counterexamples, especially on the circle, that we have Scharkovsky theorem fails. You can have maps of period 3 and no other periods. Okay. And you can find some of these examples in the book that Professor Kumar mentioned, the Discrete Chaos book, that you can find many of these examples, okay, that where Scharkovsky theorem fails if you go to higher dimension, not real line, even circles. And so there's one extension that I want to mention here. And for those who want to do more research in this, okay, is the extension from one dimension to higher dimension, to any dimension, actually. And when we talk in higher dimension, we are talking about maps on the Euclidean spaces. Okay, because Scharkovsky theorem on the real line. So that means we are, if we want to extend it, we go to Euclidean space, R to the N. Okay. So now if you go to R to the N, not just R2, R to the N, then there are special types of maps. We call them triangular maps. Okay. Now triangular maps are maps that from Rn to Rn, but these maps, if you take the derivative of the map, the Jacobian, you get a Jacobian matrix. So the derivative of a map from Rn to Rn is a Jacobian matrix, n by n matrix. It's called the Jacobian. And that Jacobian, if it is upper triangular or lower triangular, then the map is called triangular maps. Okay. Now, triangular maps are the ones that Peter Kloiden basically worked on it, and he was able to extend Scharkovsky theorem to higher dimension, but for this special type of maps, which you call triangular maps. So what is a triangular map? Again, is triangular maps are maps in higher dimension, Euclidean spaces Rn to Rn, where, of course, they are differentiable maps, and where the derivative or the Jacobian matrix, which is the derivative of these maps, is upper triangular or lower triangular. Okay, and that's Scharkovsky theorem extend there, so it's valid. In another direction, I did with my former PhD student from Portugal, is Raphael Lewis. He did an extension of Scharkovsky theorem to periodic difference equation. It was published in 2006. So, and I think he did some other work after that with some people from Spain, and they improved that result. So periodic difference equation is a special type of non-autonomous systems, but instead of have infinitely many maps, we have finitely many maps that repeat. Okay, and the extension here of Scharkovsky theorem is not as perfect. It's not like 3 implies 5, 5 implies 7, etc. It is a little bit more complicated. Okay, and so the question is, can we extend Scharkovsky theorem to regular maps? So, and this question, many people looked at it, and it is rather a difficult question, but we have a few conjectures here. One of these conjectures is that certain maps, I will give them a name, amiable. Amiable maps means friendly maps. These friendly maps have the same type of structure, and we conjecture that Scharkovsky theorem will actually be valid for these planar maps, means two-dimensional maps on the plane. And some of these maps are known into mathematical biology. One of them is called Ricker map, Ricker competition model or map, a two-dimensional map. It's exponential type of maps. The second map is what we call logistic map, but that's not the 1D logistic map that's known. It is two-dimensional logistic. And the third one is really coming from game theory. It's called chronoduopoly game model. And we found that these three maps have similar structure. And these maps will have similar structure in the sense that we'll have two things we conjecture that will be valid. One is that the Scharkovsky theorem would actually work here, period. The Scharkovsky order of integers will work. The second thing is something that I've not talked about today, which is Feigenbaum number. Feigenbaum number is a universal number for all maps, unimodal maps in 1D. Unimodal means one hump, like this, like logistic map. Okay, so we also conjecture that for these amiable maps, the Feigenbaum number will also be universal. We were not able to find that universal number, but I'm sure some of you young people and not so young will be able to do it. That's the other thing is what we call Allright-Singer theorem. So what is Allright-Singer theorem? Well, there is Singer theorem by itself and Allright-Singer. And most people think it is Singer theorem, but Allright actually published his result a few months before Singer. Okay, and Allright-Singer basically talk about global stability, global attractivity in one-dimensional maps. Okay, so if you have a fixed point of a map in 1D and is globally attracting, then you would like to know what criteria you can give for that. And Allright and Singer, both of them discovered something called the Schwarzian derivative. And for those who are not familiar with that, again, you can check my book, Discrete or Devaney Dynamical System book, and you'll find in my book, I have a different Singer theorem, but basically Schwarzian derivative is defined there. And the Schwarzian derivative requires that the map at least is three times differentiable, because you require to have f double prime, f triple prime, and f double prime, and f prime. So Allright-Singer theorem says that if the Schwarzian derivative is negative and the absolute value of the derivative of the map is less than 1 at the fixed point, then that fixed point is globally attractive. Now, the situation now, can we extend this beyond 1D? And it is really one of our major conjecture here is that Allright-Singer theorem will be extended to the maps that I talked about, amiable map, two-dimensional maps that share similar properties. The problem here is that what would be the corresponding, the analog, the counterpart of the condition of the Schwarzian derivative is negative. So far, nobody is able to find the analog of Schwarzian derivative for higher dimension. more than one dimension. Also, can we extend the I'm sorry, extend the organized singular to non-autonomous, even one-dimensional non-autonomous system? That's still unknown. Singer theorem was extended by my student in his PhD thesis, where you have single theorem, not all right single. Single theorem says if you have a critical point where the derivative is 0, if you have a locally attracting fixed point, and around it you have a critical point, the critical point must actually be attracted to the fixed point. And if you go to 2-dimension at least, you don't have one point, critical point, but you have a set of critical point in 2D maps. And this will be called the critical curves if the maps are reasonable, nice. And the theory of critical curves, or the set of singular points in this case, is of active research at this point, and they actually will determine the global dynamics of the system. We're talking about 2D now, 2D maps. And we have done some of that with some of my students, especially Rafael Lewis from Portugal, and Cabral Borrera from Brazil. And we are going to continue working on that set of singular points, critical points, or critical curves in this case, and how this would affect the dynamics of the system. One of the things that we found in non-autonomous system also, they are focusing in something called pullback attractors. Okay, pullback means negatively, going backwards. What I think is probably better to look at the forward attractor instead of pullback attractor. Okay, and the only way to do that, in my view, is really to start working on embedding this non-autonomous system into autonomous system using the SKU product idea that I mentioned. And then once you do that, then I guess you can talk about forward attractors, the usual attractors. Okay, so the usual attractor is you iterate forward, of course, not backward, the future. Okay, and the partial results were done by Ziad Al-Sarawi, who was also my former PhD student. Ziad Al-Sarawi did this forward attractors, but for periodic system, non-autonomous system. So still the open question is, can you do this for general non-autonomous systems, forward attractors, using the idea of SKU product? This is an open question that I hope some of you will be able to do that. And thank you very much for your listening. Please, if you have any questions, please let me know, and I will be happy to answer any of your questions.
Professor Saber, I could not see any questions in the chat box.
I do not see either. So maybe maybe people are still early morning,
Yeah, I'm not sure.
or the subject is not of great interest to people.
If there are questions, if you don't mind, let them ask to mail you. Is it okay for you?
Yeah, of course. Yeah, they can mail me. They can. I'm available, of course, all the time.
Okay, so let me thank Professor Saber for his informative and enlightening lecture. As you all know, he is talking from Trinity, Texas, United States of America, and the time over there is 12:30 midnight on 23rd. So without sleeping, he is giving the talk for us. So thank you, Professor Saber, for your enlightening and informative talk. On behalf of the organizing committee and on behalf of all the participants and on my personal behalf, I express our sincere gratitude to you. Professor Saber, thank you.
Thank you all for listening, and I hope I can go next time, be in your place physically and celebrate this. Okay. Good night. For me, good night, but for you, still morning time.
So there is some announcement for the participants. The next session will be at 12 o'clock from 12 to 1:30. The session will be handled by the speaker is Professor Vijay Nadarajan of Indian Institute of Science. He will be speaking on topological data analysis. I request all the participants to join before 11:45 today in the same link. The link is always same for the session, for the series on topology. So please join before 11:45 for the session, which will start at 12 o'clock. And the speaker is Professor Vijay Nadarajan. He will speak on topological data analysis. Thank you. Thank you. We'll see you in the next session. Thank you.